So this morning, we have a special guest of honor, Professor Paul Duffell. And Professor Paul is a member of the faculty here at Purdue and the Department of Physics and Astronomy. He is what you would call a theoretical physicist. So that means he doesn't really do observations and experiments, although he knows a great lot about those things. So we'll poke his brain a little bit later. And we have some great TAs, some familiar faces and a couple unfamiliar. So we welcome all the TAs. At this point, turn it over to Professor Paul Duffell and let him explain a little bit about where we're headed this morning with knowing about exoplanets. Paul, you want to go ahead?
Yeah, thank you very much, Dave. And I want to mention before because I might forget it, I was good if I try to mention this at the end, but I want to say thanks so much for putting this together. Like, one of the great things about Purdue is we have a Dave, we have somebody devoted to coming up with great ideas of ways to engage with the community and to, channels for people to ask any questions they have of professors and for us to talk about our research. So I think it's great. He does a lot of work putting it together. So thank you very much. So my name, yes, as Dave mentioned, I'm Paul Duffell. And by the way, I am a professor at Purdue, but you don't have to call me professor if you don't want to. You can everybody calls me Paul. I liked Dave calling me Professor Paul. I thought that was pretty good. But yeah, I'm not particular about it. If you feel uncomfortable calling me by my first name, that's fine. You can call me Professor, but I don't mind informality. But yes, so my name's Paul Duffell, and I'm a professor here, and I work on a wide range of topics in astrophysics. I work on a little bit of everything. I do theory. Actually, Rana Deep is my grad student who's here. But yeah, in our group, we work on all kinds of problems: planet formation, supernovae, black holes, all kinds of different types of problems in astrophysics. So if you have a question not related specifically to this, that's fine. I'm happy to, I don't know everything, but I'm happy to happy to answer what I can. So today we're talking about exoplanets. And oh, by the way, this is, there's not a lot of you, but I really would, it'll make things go a lot more easily if we're interactive as possible. It makes me more comfortable if people are answering my questions. So I hope you guys are willing to jump in and answer questions whenever I have them. So my first question is, have you heard of the term exoplanet? Do you know what exoplanets are?
Yes, I've heard of it before.
Okay, so what have you heard?
It's just a planet that doesn't orbit our sun. Basically.
Exactly, that's right. That's exactly right. So an exoplanet. So it used to be all we had were the 8 planets we have in our solar system. Well, we used to have 9, but now we have 8. It used to be there were just those 8 for us to look at, but now with modern technology, we can actually look at planets orbiting other stars, which is really incredible. So I guess I'll move on to the actual experiment we're going to be doing today. And what we'll get in a minute, we'll give you a link. Oh, I need to share my screen in order to do this. Hang on, here we go. So in a minute, we'll give you a link to this web page. But basically what you'll do is you'll go onto this, and then the first thing it'll do is it'll ask you I will prefer to call it a scenario, but which scenario would you like to use this simulation? That's fine. And you pick 1 through 5. So it'll depend on, will depend on what room you're in or something, but we'll pick a scenario. So I'm just gonna pick 4, but that's the first thing that happens. And then you'll get this image here, this actual kind of movie here. And actually, you can also put this in full screen. Can everybody see what is on my screen?
Yes.
Yeah, I can see that.
Okay. So what am I looking at here? By the way, you can scroll to zoom in on this too if you want.
A little planet orbiting a star, I guess.
Yeah, that's good. Right. I mean, it's not obvious, but that's right. That's what this is meant to be sort of an image of, is this planet orbiting. Whoa, looks like it moved really fast there for a second. It's because I was zoomed in. That's right. It's a planet orbiting a star. Okay, and I'm going to try to pause it and catch it so you can see the planet, but that'll depend on me clicking just right. There we go. There you can see both the planet and the star now. Okay, and so what else is on this page? Does anybody?
On the luminosity chart where it goes down and the planet passes in front of it.
Good. So there's a graph here of luminosity. Okay, good. I'm gonna, just because I don't want it just to be one person answering, as much as I appreciate, Daniel, that you're answering a lot. I very much like that, but I don't want it to be just one person, depending on how many people we got in the room. If other people can jump in too, that would be great. Okay, so we got a graph of what does it look like it's plotting?
The luminosity and brightness.
Right. Yes. We're kind of conflating those two concepts, but yes. So we'll just imagine it's brightness, and then as a function of what? In other words, what is on the x-axis here?
The time.
Yeah.
Earthly?
Good. Sorry, I think it's easier. Yeah, it helps me know that people are following rather than me just monologuing at you. Even if the question seems simple, by the way, you can also do this trick where you put your cursor on here. It'll tell you the actual values at any point. So that could be kind of handy for you. So how are we going to use this to figure out how is this graph related to this animation? Anybody can answer that.
Paul, would you mind pausing that one more time again?
Yeah, I'm happy to. Let me try to catch it so that it's at a convenient. Oh, I missed it. That's okay. Well, I paused it anyway.
Okay. Would you go back to the graph and put your cursor down there? And yes. Let's just take a look at those numbers that we see. What we've got two numbers there. One looks like one's in scientific notation, and the other is a decimal number. Or do we know what? Do we want to talk about what those numbers represent?
Yeah. So can somebody tell us what this means, or can somebody figure out what this means if it says 1.11 E3, 0.987? What does that mean?
Oh, 1.11 E3. That's the days, correct?
That's right. That's right. At that point, upstairs. And then what? And
then the 0.987 is the brightness of the star.
That's right.
At that time.
That's right, exactly. Oh, well, it's not necessarily the brightness at that time. It's whatever the brightness is in these crosshairs. So as I move this thing around, it just tells me the value on the graph. So it doesn't tell me necessarily what value is being plotted here. It just tells me where my cursor is.
So if you wanted to know the brightness at one of those peaks or one of those dips in the graph, you could do that just by putting your cursor right at the very tip of like right there. And then that would give you, and if you look,
you can read the number.
Yeah.
All right, how are we going to use this to relate? How are we going to relate this graph to this movie? By the way, if this graph ever, if you keep making this graph can sometimes get out of control. It's always possible to either refresh the page, or I think there's a button you can just have it rerun it, starting over. And then I'm going to go back to full screen. So you can always start it over if it seems to be getting out of control. All right. So how do we use this graph to learn something? How do we relate the graph and this image here? If we look at it, what's happening in the graph at the same time as in the movie?
It looks like we have a chat. Does it have to do with how bright the star is during certain periods from Nelly?
That's
the orbit is also involved.
No, this is good. Yes. So how bright the star is at different times. That's right. And so why does the brightness of the star change?
when the planet passes in front of the star, it dips just ever so slightly?
Yes, it's very good. Ever so slightly. You can actually see, if you notice, the y-axis goes between 0.986 and 1 here. So it's a really tiny dip. But it looks, if you zoom, it's a little bit zoomed in, so it looks like a big dip, but it's a very, very small change in the brightness of the star. But if you can measure that change, good. Then how can we use that, relate that to understanding the planet? Another way of putting that is, if you can see something like this in a star, then that's evidence that there's a planet there. But can we learn more about the planet from the dips? Like, for example, would different planets give different types of dips?
Like you can tell the orbital period and like there's different aspects. Maybe could you tell the diameter of the planet? Maybe. I'm not sure.
That's exactly what we're going to do today. Very good.
Paul, before we go ahead, let's just for fun ask.
Yeah.
If Daniel said those represent the orbital period, if we take the cursor and look at one peak to the next, we could actually calculate then the time between the times that the planet passes in front of the star, which you get my point? So if we have the number of days at that peak right there, or any peak, so there's those are small numbers, 1.55 times 10 to the third. And then we go to the next peak and we have 1.91 times 10 to the third. So that's 1,910. And what do we get if we subtract those? So we had 1,550 and 1,910.
360 days.
Oh, okay. What does that mean? If you're going to explain that to a fourth grader, what does that mean? We have an orbital period of 360 days. What does that represent?
Its year is roughly the same as Earth's year.
Yeah. So yeah, that's the magic word. It represents 1 year for that planet, which is coincidentally is somewhat similar to Earth, to our own year time, number of days. Okay, great. Paul, I'll turn it back to you. I just wanted to make sure we're on the same page.
Yeah. I'm not sure I had much left to say, unless I was missing something that I haven't explained.
Well, I think we can go to breakout. Everybody,
All right.
This is Dylan, and he'll take us from here, and we'll go through the model.
Perfect. So let's pull up one real quick. And which one do we want to start with, Dave? What are you thinking?
Well, why don't we start with number 5?
Let's do number 5. Both of these in the shot here. Okay, so I'm gonna pause it right here. All right, so this is number 5 for anybody that's following along. So let's just kind of go through the steps again. Start with the period, like we just calculated the orbital period.
I'd like to hear what from our students. When you look at these numbers, what
I got 15.5, really close.
But yeah, it's my cursor's a little bit off, so we'll start with that. And then the next peak over, I have the second point pulled up, so if somebody wants to let me know what they got for their orbital period, I'll use that for my calculation.
I got 7 days.
7 days. So we'll have about 7 days now.
Dylan?
Yeah.
Let me just interrupt you here for a minute.
Yeah, go ahead. Go ahead.
We have an orbital period of 7 days. Does that seem peculiar to anybody? What do you think about that?
Sounds awfully short.
It does, doesn't it? So let's explain it to a third grader. If a planet has an orbital period of 7 days, what does that mean? Describe what's happening. How would you explain that?
It goes around the star in 7 days.
Yeah. So every 7 days, the planet makes one rotation around the star. That seems pretty quick. So as maybe a further question, think about this. What would you maybe assume about the relationship between the star and the planet if its orbit is so fast, so little time? You think it's where would the planet be relative to the star?
Probably closer than Mercury is to our sun.
Sure, this would be like, Mercury has its distance to the sun is shorter, its orbital period is shorter. The distant planets, the gas giants, have much longer orbital periods. So there's a relationship between how close the planet is to the star and its orbital period. I think this is a real interesting example. Dylan, sorry for the interruption.
No, you're perfectly fine. It was a good point. So we're gonna move on to the next box, and it is delta L, or change in brightness. So really quickly before I dive into that, have you guys ever seen the delta symbol before? Are you guys that far along in math? Do you know what it means?
I've seen it in science a few times before.
Yeah, go ahead. What does it mean?
It's just a change from like where you start.
Yeah, you're exactly right. It's just the symbol that we use to represent as change. And then L in this case is going to be, any guess for what that means?
Luminosity.
Yep, perfect. So this is going to be the change in luminosity. So going back to our graph here, this one's a little bit peculiar because you're going to have different depths. It's not going to matter. They're all on the same because it's such a small change. So they look different when it's this far zoomed in, but they're all about the same. So, hovering the cursor, we're going to have our baseline luminosity is going to be 1. And then is everybody kind of getting the same thing where it drops down to the number that I have shown right now?
Yes, I have the same number that you do.
Yep. So the important thing here to remember is we're calculating the change. So it would be the beginning luminosity minus the luminosity that we have now. So if you would like to do that calculation, go ahead and let me know what you get, and I will put that down here. Did anybody get a number for that one?
Dylan, bring your cursor back down. Let's get another look at
Yeah.
what we're subtracting. Okay, so
Yeah, they're posting it in the chat.
okay.
0.011. Yep, got it. So that looks right to me. So then we have this third box that is planet radius. So how are we going to get from basically what we have now to getting the radius of the planet? Does anybody have any ideas of how we're gonna get to that? I also do want to point out that on the chart we do have some information about the star itself. So think about how that is going to come into play when we calculate the radius, and let me know what you think.
So Dylan, just to be clear, so we have, you refer to the chart. We've got some information on the chart.
Right.
Okay, so you're asking, we're thinking about the radius of the planet. So how big is it across? That would be diameter. Radius would be half of that. So we're interested in a dimension of the planet. We have a dimension of the star. Both are radii. Radius is radii. We have the change in brightness. Okay, so remind us again, what's your question?
What's my question?
Yeah, what are you asking us to do?
Yeah, I want you guys to think about how we can use this information, the change in brightness and you know, the information of the stars and the radius of the star and how we can possibly calculate from that. Does anybody have any ideas for that or any questions? Actually, switch over here real quick. Maybe.
Maybe I can ask the question in a different way. So we instinctively, it seems that the size of the planet should matter, should affect the shape of this graph. So why is that? So, you know, if you have a bigger planet, how would that change the graph? If you have a smaller planet, how would that change the graph?
Maybe the dip would be like more of a point rather than kind of like a flat line if it was smaller.
Right, so the shape could be definitely affected, but there's even something more in terms of the numbers that you're measuring. How would that affect it?
May I chip in something? For the students, try to think, why is there a dip? Like, what is the planet doing for the dip to be there? Paul, you're muted.
Yeah. Sorry,
Yeah.
I'm an old man, not knowing that I'm on mute. Okay, yeah, we have Mari in the chat is said if you have a bigger planet, then the change in brightness is bigger. Does that make sense to people? So when you measure that depth of that delta L, somehow we can hope to relate that to how big the planet is. Maybe we should back up and ask, okay, so we get the sense that bigger planets make bigger dips, right? So why is that? How would you compute how deep the dip is, or you know, how would you even begin to compute how deep the dip is as a function of the planet radius? You don't have to have the complete answer, but just some picture for from roadmap for where you get started. How do you relate it to the radius?
The radius of the planet would somehow relate to the starting luminosity over change luminosity, right?
So why is it? Why does the radius matter?
Because the bigger the planet is, the more change will happen because it's blocking more of the light.
Because it's blocking more of the light, right? Exactly. So how much of the light does it block? How do you figure that out? Oh, I guess I should ask a different question. If you knew the radius of the star, if you knew the radius of the planet, could you figure out how much of the light it's blocking?
I also kind of thought of it like this. If the radius of the planet is larger, then delta L will also be larger, right? So we have the radius of the planet in the numerator, because if that radius increases, then delta L, because it's also in the numerator here, that will also increase. So that's kind of how I thought about it, and how it made sense to me. I don't know if that would make sense for everyone else, though.
So then the next step would be, we have an equation now, but how do we get we are missing a part to this equation.
This equation isn't
we're not quite there yet.
Not quite there yet. Yep, that's right.
So this gives us a relationship that would give us correctly that if you make the planet bigger, you get a deeper dip. But it's not obvious that this is the correct formula. And in fact, it turns out it's not the correct formula. We're going to get the correct formula in a second. But if you think about it, because there's lots of formulas we could write down on the right-hand side where the planet would get bigger, or, you know, that would get bigger as the planet gets bigger, right? So it's not obvious what we should have on this right-hand side. The question we're trying to ask is geometry, basically, right? You know, we said radius or diameter; those are both, you know, it's true. If you make it bigger, then you'll get a bigger dip. But so, what should the formula involve? Should it involve the diameter or radius, or should it involve some other geometric quantity related to the radius?
Maybe the area of the planet.
Good. So what's the area of the planet?
Pi r squared.
Right. And just to clarify, why the area? Why did we say that?
Maybe because the radius, if a planet was more squished, the radius would change depending on it. So if you just had the area of the planet, or I don't know.
Let me try to explain it. Okay, let's assume hypothetically, it's not possible, but let's say we have a planet which is flat, a flat planet. So will that cause the same dip as a circular planet or a spherical planet? Anyone? Okay, the question I'm trying to put here is, let's say Earth was flat. So someone looking far towards like Earth blocking the sun's light, do you think a flat Earth and a spherical Earth would cause the similar, at least the shape-wise dip, like the same depth? Or let's say you're looking from the bottom where the planet is like revolving, but it's like you're looking down up. So you have a planet, star here, and the planet is going like this instead of like this. Does that make sense to anyone? Yeah, exactly. Exactly. How about these two different planets, a flat Earth and a spherical Earth? How is the dip different between them?
The flatter Earth would block a lot less light than the spherical one.
Exactly. So the area does matter, like the area towards us.
So good. So we get that it's the cross-sectional area basically that matters that we're looking at. So, and we correctly say that's pi r squared. So so how do you think our formula should actually look, the right-hand side? Let me put it a different way. If I multiply the radius by 2, how much does that change delta L?
It would double it.
If the radius would double, what happens to the area? So if I double the radius, then it quadruples delta L over L. So in that case, then this formula I have that we wrote up here for delta L over L can't be right, because this formula says that if I double the radius, it doubles delta L. So but if it's based on the cross-sectional area, then doubling the radius should quadruple delta L, right? So how should we be modifying this formula? We can still say delta L over L equals something, but what do we think we're going to have?
Is it as simple as thinking of using the equation? If we want to get from radius to area, is it as simple as using the equation pi radius squared?
Yeah.
Looks like
Yeah.
Nelly agrees.
Yeah, Nelly agrees. Yeah.
Okay. Well, Nelly and I agree. Good. So if we put pi radius planet squared, there's one area. And then in the denominator, pi radius star squared. Is that going to give us the ratio of areas relative to the ratio of brightness?
So we have this equation, but what we really need out of it, as we mentioned, is the planet. So go about attacking this equation to get just the radius of the planet. What would you guys do? So on the right-hand side, we have pi over pi. Those are going to be the same, like the radius. So those two, they cancel out. So it's pi divided by pi. So it's just 1.
Sure.
On the left-hand side, this one's a little bit more, maybe a little bit more confusing. Graph that we used, the L was the number, what we call normalized. So we don't have like a complicated number. It will actually just be 1, and we can think of it as just delta L on the left side to make it look a little bit nicer for us. So,
And that's because we're using luminosity. When we look at our graph of luminosity versus time, we see that it's like 0.98. So that's like a percentage or a fraction of the total luminosity, which would be 1, right?
Yep.
So that's why we can do that.
Yep, sorry, that was a better explanation. So now we have what's left is what Thomas wrote there at the bottom. So Nelly, you said rearrange the equation. how would you go about it? What would be the first thing that you would do to this equation to get to just the radius of the planet?
You would multiply our radius of the star squared to get to the other side if you just want the radius of the planet squared on that side.
I think that's a fair place to start. Do you want to write that out, Thomas? Okay, so now we have radius of the planet by itself, but it's still squared. So what's that next step that we need to take to get it just as the
Square root.
radius? Square root
The
it,
whole
perfect.
thing.
So square root both sides. And so we have an equation. So, and we also have the radius of the star. It is for scenario 5, and we also have our delta L. So now from here, we can just calculate the radius of the planet. So does anybody want to give that a shot and let us know what you get?
You can also simplify the equation just a little bit further by taking the square root of the radius of the star squared. So you get this. It gives you the same thing, but this equation just, in my opinion, looks a little nicer.
Now, that seems a little less intimidating.
What'd you get, Nellie? It might be right.
All right, it'll be easier if I don't have to look at the decimal place so I can see it in scientific notation. Let's see. 3, 5, 6, 8.
I think based on the table we found, or the calculations we did the other day, that does seem right. Yeah.
Oh yeah, it's the same thing I got. Excellent.
Whoa.
I did this a few days ago, so good. Excellent.
Yep, so great
I
job.
was like, oh, I have to count all the decimal places. Okay, good. Thank you, Nellie. I appreciate it. So excellent, great. Now, okay, so you said it seems wrong to you. Why do you say that? It seems, yeah, it does seem really large. And we said, we already put that there. Did we say, we said 10 to the 8, 10 to the 8 what? Okay, so 10 to the 8 meters. Now, when you're doing astrophysics, it's always hard to tell whether something is really big or not, because everything's really big in astrophysics. So we have to figure out whether that's reasonable, right? So maybe a good exercise is, like, for example, what if we Googled the radius of the Earth? Does somebody want to do that? Just Google what's the radius of the Earth. Not the TAs, they might already know it.
6,371 kilometers.
Okay, I'm going to just say 6,000 kilometers, okay, which is how many meters?
6 million, because it's times 1,000, or no.
Good,
Yeah.
6 million meters. So 6 million is 6 times 10 to the what?
6.
10 to the 6. Okay, so what? Okay, so that's the Earth, and then but for this planet we got 10 to the 8 or 1.5 times 10 to the 8 meters. So what does that tell us?
It's a little bigger than Earth.
It's a lot bigger than the Earth. It's like what, something like 20 times bigger? Well, even more than 20 times bigger. So what does that mean? Are there planets that are that big?
Jupiter's pretty big. It's like kind of
Jupiter's
like a
pretty
Jupiter
big. Let's Google Jupiter's radius. I don't happen to know that one off the top of my head. 70,000 kilometers, you said?
7 times
Yeah,
20 by
It
7.
was about that.
Okay, so that's 7 times 10 to the 7 meters. So what does that mean for this planet?
It's still a little bigger than Jupiter.
Yeah, it's still about twice as big as Jupiter. So what's kind of crazy about this, so the different, now we didn't have time to do all the different scenarios that we listed, but you can figure out which ones are like, like these gas giants like Jupiter, and which ones are the small rocky planets like the Earth. So that's the cool thing about it, is this thing super far away. We can't even resolve the image of the planet, but just from the dips, we can tell what type of planet it is. Does anybody have questions about this?
Thomas, do you want to stop sharing your screen? And I'm going to turn things back over to Professor Paul. He's got a brief PowerPoint that I think we'll find interesting. Paul, are you ready for your PowerPoint?
I hope so. Thank you, Dave. Let me make sure I'm ready for this.
I want to thank our students for doing so well on sticking with us and getting through that calculation. To see what we can do with a little bit of basic data is fantastic.
Yeah, I appreciate that. And by the way, again, there's only a handful of you folks, so please feel free to interrupt me. There, you should feel like there's only a few of us in the room, so you're not you're not wasting anybody's time by interrupting me and asking questions. Because I got nothing better to do. So anyway, this is actually just this first slide is just mostly looks like what your sheet said, and we sort of figured out that the amount of light being blocked is determined by the cross-sectional area of the planet. As you can see, as the planet's passing by the star, it creates that dip. Also on your sheet, there was a previous version that had also orbital radius. In other words, the distance of the planet to the star, and we didn't really talk about that, but it turns out you also can figure that one out. By the way, does anyone have a guess as to what you would use to figure that out? It's okay if you don't know the answer, but it's okay if you don't know the answer because it's a little bit more complicated. That requires a bit of physics. Here's my filled out sheet in case you care. But we had all these 5 different scenarios. Scenario 2 was actually a plan it would actually have all of these, by the way, are from using real data from real planets. This number 2 is a real one that we've known about for a long time. It's the Earth. So you may have so you would get if we had done scenario 2, we would have gotten exactly 365 days, and this is the 6 million kilometers that somebody Googled. You can also figure out the radius, an orbital radius. What I mean by that is not the radius of the planet, I mean the distance between the planet and the star. And the way you figure that out is, I made this little movie there that sort of shows the planet's orbiting. You can actually figure this out from Newton's laws of gravity. The closer in planets always orbit faster because they're close to the star, they feel more gravity, so they orbit faster. And then the further out planets orbit much more slowly. So Jupiter, it has a much longer period, and Mercury has a faster period than Earth. So if you can figure out the period, you actually can work out using Newton's laws. Basically, you can figure out how far the planet is from the star. So in this particular example, if we had done this example, we would have gotten 1.5 times 10 to the 11 meters, which is the distance from the Earth to the star. Which is what astronomers call 1 astronomical unit, is the distance between the Earth and the sun, 1.5 times 10 to the 11 meters. But yeah, the point is that this is not a to scale representation of the solar system, but it does include all the planets, and it's kind of neat to look at. But what's going on is actually how it works is the closer in planets orbit faster. Here's another not to scale representation of the solar system. All the planet sizes are roughly to scale. So you can see Jupiter is about 10 times the size of the Earth and that sort of thing. The reason I'm showing this is it's actually for a long time, this is all we knew about planets was our own solar system. In fact, we only started to be able to detect exoplanets since the 90s, since 1998. Before 1998, this was our only data point for how planets formed. This is the only data point as far as we knew, there were no other planets in the universe. It could have been that they just formed around one star in the universe, as far as we knew, because we had never detected anywhere else. And so it became very difficult for us to try to understand how planets formed. We can learn a lot more by looking at more than one solar system. For example, if you notice, our solar system has this interesting property where the small rocky planets, right? Mercury, Venus, Earth, and Mars are all the little planets that are just made of mostly rock. Those are all close to the star. And then the further out planets, Jupiter, the really big gas giants, Jupiter, Saturn, Uranus, Neptune, those are all further out from the star. And it used to be, we thought there was a reason for that. We thought that you could only form those gas giants outside a certain radius, and that because we have only this one solar system to look at, we thought that was like what all solar systems must look like. But then that changed in 1998, the very first exoplanet ever discovered. It was called 51 Pegasi b. This was not using the transit method that we talked about today. It was actually using a different method they called radial velocity, but it's okay. It's basic, but it's still, so this graph over here is showing this 51 Pegasi b in relation to what our solar system looks like. And then on the bottom here, you have distance measured in astronomical units. So 1 AU is the distance from the Earth to the sun, right? And then Jupiter is at 5.2 AU. And then so you have Mercury, Venus, Earth, and Mars. 51 Pegasi b was really, really close to its parent star. It had a very, very short period. So we determined it was, you know, at a smaller orbit than Mercury and larger than, and more massive than Jupiter. And actually, it was like the example that we looked at with that had that short period, that 7-day period, and a very large radius, right? It's I don't know. I don't think that was 51 Pegasi b. Maybe we could double check. That's something to think about. But this was the first exoplanet ever discovered, and it immediately told us that we were wrong about our solar system. We thought that you had to have the big planets further out, like that there was some reason that the small planets were close in, but immediately the very first exoplanet we ever discovered, like completely turned us on our heads and forced us to rethink how planets form. And so it's always nice to have more than one data point, but now we have a lot more data points. There's a lot of different ways of detecting exoplanets. This is an example of, this is actually showing what Rana was talking about a little bit ago. This is real transit data from a system called K232. So the top plot here shows the luminosity as a function of time, but you notice that it's messier because the star can also get brighter and fainter just on its own. It can have sunspots or things like that. And so that you have this sort of messy up and down behavior that can be a little bit hard to deal with, but it's possible if you know enough about how stars work to sort of remove that from your signal, and you can get something that looks more like what you guys were looking at, this normalized flux, which is like at 1, and then it dips to some percentage of that. So that's what this second panel is. It's a lot more like what you guys were looking at today. But it's still complicated because there are 4 planets in this system, and they've conveniently color-coded them so you can actually see that the different dips are associated with different planets. But if you didn't have the color coding, it can be kind of tricky to disentangle which dips are due to what. But so that can take a lot of work, but it's amazing because you can actually just look at these dips and sort of see the different types of planets there are, right? This has a deeper dip, so it's going to be a larger planet, and it has a 10-day orbital period, you can see. And then you can see that you have a smaller period planet, so it's closer in, and it's a smaller dip, so it's probably a rocky planet. But so we can actually we can see the whole solar system there. They're very tightly packed in. They're all very short period, but you can potentially get the data for a whole solar system with a light curve like this. So that this transit method is extremely powerful for being able to understand how these different solar systems look. Here's another example. This is a third way of detecting planets. We talked today about how it's, we don't usually are not able to resolve we don't actually see this planet orbiting the star, but sometimes if the planet is very far from the star, if it's well enough separated, it's actually possible to resolve it. So this is an example of of 4 planets that are very far from their star. And I'm just going to tell you, I'm going to point, these are the 4 planets. And I'm going to tell you for a second that those are the 4 planets that you're looking at. And you might say, well, they just look like blobs of light. I don't know if they're planets. Like there's also messy blobs here, but that's actually, this is a tricky measurement to do because you have to block out the light from the parent star. They use this thing called a coronagraph to block out the light from the star, which is where almost all the light's coming from. And then if you block it out and subtract it out well enough, you can recover these planets. But the really cool thing about this, you notice this date here is 2009. They actually took data on this between 2009 and 2016. And so you actually, this is actually not a single image, it's an animated GIF. So we can actually watch over time, as you take these multiple images, you can actually see a movie of the planets orbiting this star. This is HR 8799 is the system. And you can actually see the closer in planets are orbiting faster, just like Newton said they would, just like they do in our solar system. But yeah, they don't execute a full orbit in that 7 years because they're very far from the star. You look down here, it says 20 AU. That's the scale, 20 times the Earth-Sun distance. So they're very, very far from their star. So what's kind of neat is you have these different techniques and they are able to detect planets, they're able to detect planets of different sizes and different separations and things like that. So here's a plot showing a whole bunch of data points of different planets that have been detected. So on the x-axis, it's orbital period in days. So, and then you can see these are the planets in our solar system. So Earth here is at 365 days. And on the y-axis, it's planet mass. I didn't find a plot with planet radius. We could have tried to do that, but this is 10 to the 0 is 1 Earth radius. So there's that. And then this isn't every planet that we've ever discovered, but it's a large bunch of them. So the blue points are the ones that are detected using the transit method. So there's a bunch of them up here. These are called hot Jupiters. And the reason they're called hot Jupiters is because they are these planets that are on very short orbital periods, so very close to their parent star, but they're around Jupiter's mass. So they're gas giants that are very close to their parent star. And there's a sort of category of planets they call hot Jupiters, which was the first exoplanet ever detected was 51 Pegasi b was an example of a hot Jupiter, but we didn't call them that yet because we didn't know they existed until that one. And then if you notice, the solar system planets are all in totally different locations than the ones that we've detected. Does anyone know why that is? So most of these are like the exoplanets we've detected. So these are ones using the transit method. The black is the radial velocity, which I didn't tell you about. And then these orange ones over here are directly imaged planets, like the last panel I showed you, where you can actually see the individual planets in an image. But why do you think this is our solar system? Why do you think they're not near any of these points? Is our solar system really different from others? Does anyone know the answer to that?
Is it just because those planets, our solar system planets, are closer to us and readily available, and we can more easily characterize them? But the exoplanets, we can see ones that are more massive more easily, or have, I guess, a different range.
Right. So yes, exactly. This is about which planets are easier to detect, right? So from the transit method, one of you could tell me which planets are going to be the easiest to detect in terms of using the transit method. Like, what properties will those planets have, the easiest to detect ones?
Larger and probably closer to their star.
Very good. So larger, right? Because you get a bigger dip, but why closer? That's a little more subtle. Why closer is easier? I can just answer it for you. That's okay.
Okay. Let me try to rephrase the question for them. Let's say there was a planet which is way further away. So how long do you think you would have had to wait for 2 different dips to come? Because we cannot say anything from just one dip. We don't know if it's an anomaly or it's going to repeat or not. So if a planet is very far away, how long do you think you have to wait for the 2 dips? Again, that's what I got.
Okay.
A long time.
Exactly.
A long time. Right. So the further they are away, the longer their period is. And so the longer you have to wait to see multiple transits. And in fact, Rana's right. If you just see one transit, you can't really, first of all, you can't really be sure that it's a planet. You might just be some anomaly you saw. If you see 2 transits, even then you can't be sure. And you can measure a period, but you can't be sure that it's but once you see 3, then you can know that it's a periodic signal that you're seeing. If once you've seen a third one, then you know for sure that it's a periodic signal that's recurring every orbit. And so we really need 3 transits to be sure that it's a planet. So we need to be looking at the star for a long enough time. Also, if it's a really long period, think about it, like if it only transits once every 10 years, right? You have to catch it, right? The telescope isn't always pointed at the star. It's got to point at a bunch of stars, and you have to catch it transiting. And so it's much harder if it's once every 10 years. If it's once every 7 days, you're much more likely to catch the transit. So the very close-in ones are great for transits. Kepler, which is the main mission that detected these transits, the NASA's powerhouse for detecting these exoplanets, had a full 10-year run, which means the longest orbit you could confirm is about 3 years. So that's what sort of cuts off the maximum distance that you can get. So anyway, that's why the transits are all sort of here. And so anyway, it's true that our solar system planets would be harder to detect for us if we were in another solar system. So it may not be it may be the case that if there is an Earth-like planet, it might be hard to detect for us. But what's one other thing? If we know the orbital period of or not just the orbital period, if we know how far the planet is from the star, is there anything interesting that tells us about the environment on the planet if we know how close it is to the star?
The distance from the star could affect if it's in the habitable zone of the star or not. It's like whether it could have water on it or not.
Yeah, that's very good. That's exactly what I was fishing for. So very good. Yes. So if you're close to the star, it can be very hot, or if it's very far from the star, it'll be very cold. And so there's a sort of sweet spot called the habitable zone that Earth is in, that we think is more conducive to life forming on that planet, or for example, the ability to have liquid water on the planet. So this plot makes it look like it's hard for us to detect habitable planets, but it turns out a lot of these planets that are over here in this region that are on, oops, sorry, I shouldn't have clicked. A lot of these planets here that are on shorter orbital periods that are closer to the star are actually in the habitable zone, and the reason for that is their stars are actually not as hot as the sun. And so their parent star, if their parent star is not as hot as the sun, then the planet can be closer, and then we would be able to detect it because it's a short enough orbital period we can catch it. So there are a number of these that we have detected that we can determine how hot they are based on how hot their star is and how close they are, and we can confirm that they would be habitable planets according to our definition of life, of what is habitable. They would be capable of having liquid water and that sort of thing. Okay, yeah, Dave's telling me to wrap it up. So, but that's all I really got. So any other questions people have? I'm happy to answer weird ones you have about black holes and things. That's fine, whatever you got.
Well, Paul, that was very interesting. I enjoyed that a lot. And the students came up with some good answers, and I think followed along pretty well. So thank you all, and to Dylan and Thomas, thanks for getting through those calculations with us. It was very helpful.
1 second, Nelly just put something in chat. I think you should read, Dave.
Okay, let's see. I agree with Nelly. Today was a fascinating and interesting topic. Nelly, thank you for your further comments. Thank you all. Thank you, students. Thank you, TAs. And Professor Paul, thank you. We'll see you all next fall.
Thank you, Dave, for organizing. I appreciate it.
You're welcome.
Bye-bye, everyone.
Bye-bye.
Bye-bye.
Thank you. Bye.
See you, Daniel.
Have a good summer, everyone.
Thank you.